second tutorial of FIR on pink. In this particular tutorial, I'll introduce you to concepts like multi-channel filtering, what is a path and a channel, what does a multi-channel MAC operation look like, and how will the operation and hardware usage change for this particular multi-channel filtering FIR IP. Let's start with what is multi-channel filtering. Multi-channel is defined as multiple input streams, which means more than one input is being given to the FIR IP. The DDC would be a perfect example for this. The DDC has two outputs, I and Q, which stand for in phase and quadrature respectively. These I and Q are considered as output streams from the DDC but will be an input stream to the FIR IP. But instead of using two different FIR IPs, we will use only one FIR IP to do two filtering or filtering for two different input streams. Now you may ask, how will this be done? This will be done in a TDM fashion. Let me explain further. TDM stands for time division multiplexing. Let's look at a timing diagram. I have input from two particular input streams. Let's go back to our DDC example itself. Let channel 0 be I and channel 1 be Q. I have three valid inputs, which is C00 or the 0th sample of the 0th channel. Then I have C01, which is the first sample of the 0th channel. Next, I have a second input channel which is named channel 1. Over here, it is named as C10. This follows the same nomenclature, which means this is the 0th sample of the first channel. In case I had a fourth valid input on the input channel 1, it would be named as C11. Using the nomenclature, it would mean the first sample of the first channel. Now, my output to this would be in stream, as FIR is a stream, works on stream protocol. So the output of this would be in a TDM fashion. The output channel over here is the input to my FIR IP. It would be in this particular fashion. C00, which stands for 0th sample of the 0th channel. C10, which is the 0th sample of the first channel. And C01, which is the first sample of the 0th channel. This concept of interleaving is known as TDM or time division multiplexing. Well, a question may naturally arise on how a multi-channel FIR IP would look like, and how does Vivado manage the two channels output and calculates them correctly if the convolution equation requires a reversed window of input? Well, let's start with the first question. The multi-channel MAC operation looks something like this. Over here, the Z 1 represent a delay line. The CH1 data represents channel 1 and CH2 data represents the data on channel 2. Over here, Z1, Z2, Z3 and Z4 are delay lines for channel number 1, while Z5 to Z8 are delay lines reserved for channel 2. Next, we have a select line. Over here, the select line has two components, 0 and 1. The 0 over here corresponds to the channel number 1 and the 1 corresponds to the second input channel or CH2. My in case is select line 0 is selected, then the output would be the data on channel 1, and in case 1 is selected, the output would be the data on channel 2 or the computed data on channel 2. Next, there is a 2 into 1 mux select line that does the accumulation for us. This is a general structure of a 2-channel 4-tap FIR IP. The 4 over here represent the coefficient numbers or the number of coefficients in the given coefficient set, and the 2 channel 1 and channel 2 represent the multiple channels of the multi-channel filtering. The output of the 4 muxes are generally added to give the output, but the select line determines the output is from channel 1 or channel 2. Let's look at a dry run to help you visualize it better. On clock cycle 0, my input would be CH00. This follows the same nomenclature as the previous example, which means the 0th sample of 0th channel. This uses a delay line of L1. L1 over here represents the delay line for channel 1, and the L2 over here represents the delay line for channel 2. And the output would be a dot product between H0 and X00. X00 over here represents again the input to the FIR IP of the 0th sample from the 0th channel with the coefficient for the first channel, or the 0th coefficient for the coefficient labeled for the first channel. Let me clarify this better. On the next moving clock cycle, I have input from the second channel or channel number 1. This also sends their 0th sample. But instead of using delay line L1, they will use delay line L2. Now, my output over here would be Y10, or the output for the 0th sample, but from the first channel. Over here, it will be a dot product between the second coefficient set, which is meant for channel 1, and given on the channel 1 or the 0th sample on channel 1. Similarly, since the input follows a TDM fashion, we will now go into channel 0's first sample, which will use the delay line L1, and the output would be Y01 with two dot products being added, H0 x00 and H1 x00. On the third clock cycle, I will have an input from the first channel's first sample using the delay line L2, which will give me an output of Y11, which is H-0 and X10 being dot producted, and a dot product between H1- and X11. The X10 represents the 0th sample on the first channel, and X11 represents the first sample on the first channel. The lower number over here always represents the channel, and the number in the bracket represents the number of sample. But this doesn't mean there are two FIR IPs in use. There is only one FIR IP in use, but we use different delay registers which are given over here, due to which our hardware usage increases, but this is done to keep track of what the channel does and what channel the data belongs to. Apart from this, Vivado also stores these outputs at a different memory location than each other to further avoid chances of incorrect outputs. Hence, due to these reasons, memory and hardware usage does increase when it comes to multi-channel filtering, but the increase isn't too significant. Look at how the hardware utilization would change for a multi-channel filtering FIR IP. Let's continue with previous examples but with slight changes. Here I have an 8-tap filter, but instead of one channel we have 4 channels now, where each of this channel still works at 12.5 MHz, and the clock frequency still remains as 100 MHz. If my clock frequency is 100 MHz, then my clock period turns out to be 10 nanoseconds, and the channel period turns out to be 80 nanoseconds. The number of clock cycles that I would get per coefficient is 8, but this is where the calculation changes. Now, instead of 8 clock cycles for the entire one channel, we have to divide it among 4 channels. So effectively, the FIR IP now has only 2 clock cycles to do the entire convolution operation for 8 taps with the present output. Now, this would require 4 DSP slices to do the work and an extra 1 DSP slice to do the accumulation, which brings out a total to be 5 DSP slices. Let's look at example number 2. Now, instead of channels working at 12.5 MHz, it now works at 25 MHz, and rest of the conditions remain same, that I have 4 channels and 100 MHz of clock frequency. My clock period is again 10 nanoseconds, but my channel period changes to 40 nanoseconds. and the clock cycle that I receive per channel goes down to only 1. So effectively, I have only 1 clock cycle per channel for the present input or per input. So the FIR now requires 8 DSP slices to calculate the output. And since they're all being calculated in the same clock period, no further DSP slices are required for accumulation, as these accumulation calculations can be done via tree adders or fast carry chains. Look into what is a path. A path is defined as an individual processing route within a channel that handles a specific portion of the filtering operation. Or it can be defined as each path in a multi-channel FIR represents a processing subunit that applies filter coefficients to a subset of inputs of the particular input stream where these paths occur concurrently. Let me explain it better through an example. If I had to draw a diagram for a 4-channel FIR, it would look something like this. This would be my channel 1, this would be my channel 2, this would be my channel 3, and this would be my channel 4. Now, since these flow in a TDM fashion, the first input would come from channel 1, let's name it A. In the second clock cycle, the input would be given to channel 2, let's name it B. In the third clock channel, the input would be given to channel 3, let's name it C. And on the fourth clock cycle, the input would be given to channel 4, let's name it D. Now, this pattern would continue to follow. In clock number 5, the input would be again given to channel 1, let's name it E. Now, for clock number 6, channel 2 would be activated with F and then G and then H. Similarly for clock cycle 7 and 8. This is what a 4-channel 1-path FIR diagram looks like. Now if we switch to a 4-channel 2-path FIR, you would realize what I was talking about. Now instead of only A being processed in 1 clock cycle, I have 1 input and 1 output over here. But for 4-channel 2-path, I would have A1 and A2 being processed over here. For second clock cycle, my channel 2 also has 2 paths and will process B1 and B2. For channel 3 and clock cycle 3, I would have C1 and C2 being processed. For clock cycle 4, channel 4 will be used and it will process D1 and D2 simultaneously. So, each path over here is a processing subunit. It does not process the entire input, but it processes a part of it, a subset of the input is being filtered. is what this particular line says. It applies the filter coefficients to these subset inputs of only one particular stream. So channel 1 will process all the A inputs, channel 2 will process the B inputs, channel 3 will process the C inputs, and channel 4 will process the D inputs. So it will process or apply filter coefficients to the subset of inputs of only that particular input stream where these paths occur concurrently. By concurrency, I mean A1 and A2 occur simultaneously. These paths where A1 and A2 are being processed occur simultaneously. So at every clock cycle, instead of one input and one output, I now have two outputs, but I also need to give now two inputs. The trade-off for these increased number of outputs is the hardware utilization. We will look more into this in the upcoming tutorials. Thank you.